Hello, my name is Noemi Glaeser, and in this video, I'll be telling you about our FC2024 short paper entitled Naysayer Proofs. This is joint work with István and Joseph Bonneau. An important limited resource in blockchain systems is computational power. On-chain computation is very expensive, and so in recent years, a lot of it has moved off-chain to services like Starknet, zk-Sync, Aztec Scroll, and others. They will perform this computation off-chain, and only proofs of correctness are stored and checked on-chain. This is called a zk rollup, and the succinctness property of the snark proofs guarantees that it's pretty efficient to verify the correctness on-chain. A further optimization is what's called an optimistic rollup. Here, the insight is that we might not even have to check the computation on-chain. All of these services are very strongly incentivized not to cheat, so we should just trust the computation outputs that they tell us. Other parties in the system should be monitoring and checking for cheating, and when they do detect it, give what's called a fraud proof. In more detail, the verifiable computation paradigm exemplified by zk rollups works this way. So here, the rollup services are represented by these unicorns. They're also the prover. And they perform the computation, in this case, cubing off-chain. So here they compute 7 cubed off-chain, and then they post the result, y, and a proof of correctness on-chain. And in the zk rollup case, we verify y pi, and if this check passes, we accept the result y. In the case of fraud proofs, like optimistic rollups, there's no proof. We just post the result y on-chain, and it's provisionally accepted if nobody disputes it within some time t. Otherwise, if within time t somebody notices something incorrect, they can say, actually, y is not the correct result. And in this case, we can resolve the dispute in one of two ways. So first, in the non-interactive case, we simply do the full computation on-chain. So we compute 7 cubed on-chain and check whether the result equals what the prover told us. And if not, we reject the original y. In the interactive case, the prover and the challenger engage in what's called a bisection game to find the exact step of the computation that they disagree on. So in this case, 7 times 7. And then only this step is re-executed on-chain to determine who was correct. So in this example, we re-execute 7 times 7 on-chain, find that it does not equal 48 as the prover claimed, and again, we reject y. In this paper, we introduce a new paradigm we call Naysayer proofs. So in a Naysayer proof, again, we post y and a proof of correctness pi on-chain, but there's no verification algorithm run on pi on-chain. So again, we do this optimistic acceptance. If no one disputes within time t, we simply accept y. Otherwise, a challenger, which we call a naysayer, can come along and say, no, actually, this proof pi is incorrect, and I will give you another proof pi nay, proving that verification of pi would fail. And then the naysayer proof pi nay is what is verified on-chain. And if that passes, we reject y, otherwise we still accept y. So naysayer proofs save work in two different ways. First, we only do on-chain computation in the case of a dispute, just like in the case of optimistic rollups. But secondly, in the case of a dispute, we actually run this verify nay algorithm instead of verifying the original proof. And the idea is that verify nay should be cheaper than verify. There's also storage considerations, which we'll talk about at the end of the presentation. So as I mentioned, like optimistic rollups, naysayer proofs rely on an optimistic assumption. Specifically, we assume there's bounded communication delay in the system. The blockchain is censorship resistant, and there should be at least one honest party willing to challenge incorrect proofs. So in this table, you can see a comparison between these three approaches from the previous slide. In the case of verifiable computation, we avoid this optimistic assumption. It's completely non-interactive dispute resolution. However, we do have to run this original verify algorithm on chain, which it's, again, still less expensive than doing the full computation on chain, but it could still be somewhat expensive. And finally, the decision to accept or reject the value y is independent of the witness. Fraud proofs can be either interactive or non-interactive, but in any case, they rely on this same optimistic assumption that I was talking about. They avoid the need to run the verify algorithm on chain, but they do rely on access to part of or all of the witness to resolve any disputes on chain. And finally, in this new paradigm of Naysayer proofs, we again rely on an optimistic assumption, but resolution is non-interactive. We don't have to run verify on chain, we run something cheaper, and there's no need to know the witness in order to resolve any disputes. Just to give a little bit more intuition, here's a toy example. Say the verification algorithm would include checking this product AB equals C. So for example, the prover claims that these two big numbers multiply to this other big number on the right. So in the Naysayer paradigm on chain, instead of actually verifying, instead of running this verify algorithm, we'd just say, okay, probably it's true. If no one disputes it, we'll just say it's true. But a naysayer could come along and say, hey, actually, even if I just look at these last two digits, 8 times 4, it's pretty obvious that 8 times 4 mod 10 does not equal 4, should equal 2. So the naysayer proof is quite simple. It's just a proof of this short statement, 8 times 4 mod 10 is not equal to 4. And verifying this proof is constant time. It's very short and small, compared to actually running this original verification algorithm, which involves this big multiplication. So let's take a step back and formally define naysayer proofs. So naysayer proof is defined with respect to some base non-interactive proof system pi. And the naysayer proof is a tuple of 3 PPT algorithms. A setup algorithm that generates a CRS for the naysayer proof. A naysaying algorithm that, given some statement proof pair of the base system and potentially some auxiliary information, produces an output, a naysayer proof as output. And then a verification algorithm which checks the naysayer proof with respect to the statement proof pair that it's trying to dispute. We also define standard correctness and soundness properties. So correctness says that for all invalid statement proof pairs of the base system, we should be able to output a naysayer proof that rejects pi. And soundness says that for all valid statement proof pairs of the base system, it should be infeasible to produce a naysayer proof which rejects pi. The trivial construction of a naysayer proof is a single bit indicating the intent to naysay, and then verifying the naysayer proof would just be running the original verify algorithm. We say a naysayer proof is public or publicly naysayable if there's no required auxiliary information to naysay a proof. You just need the statement proof paired. And we say a proof system pi is efficiently naysayable if there exists some corresponding naysayer proof system pi nay, so that verifying a naysayer proof is asymptotically faster than verifying the original proof. If verify nay is only concretely faster, we say pi nay is a weakly efficient naysayer proof. We show that every NP language L has a naysayer proof system with constant size proof and constant time verification. This follows from the Cook-Levin theorem, which says that any NP language L has some circuit C, so that if the statement X is in the language L, then C evaluated on X will output 1. So in this example, a proof of membership of X in L would simply be a satisfying wire assignment for the circuit C, outputting 1. And a Naysayer proof, if pi is actually incorrect, there must be some gate in C where the wire assignment is not correct. And so a Naysayer proof can simply be pointing to the index of that gate, and verifying that Naysayer proof would simply be reevaluating that gate. So this is constant size and constant time. This also implies that every efficient proof system pi, so every proof system with a polynomial time verification algorithm, has a succinct Naysayer proof, because you could represent the circuit or the verification algorithm pi verify as a circuit and apply this theorem to that circuit. So now that we've formally defined Naysayer proofs, let's look at some concrete applications. In general, any proof system with some kind of repetitive structure, multiple identical rounds, recursion, and so on, is efficiently Naysayable. So here we give some examples. First, the Frey polynomial commitment opening proofs, 2 post-quantum signature schemes, crystals, dilithium, and Sphinx plus, and verifiable shuffles. You can see in the table that in the case of the Frey opening proofs, Sphinx, and the verifiable shuffle, the Naysayer verification algorithm here on the bottom row is asymptotically faster than the original verification algorithm. So these are efficiently Naysayable. In the case of crystals dilithium, Naysayer verification is only concretely slightly faster than the original verification. So this is only weakly efficient. Finally, let's talk about storage considerations. Many blockchains have multiple tiers of storage. For example, Ethereum has persistent storage, which is the most expensive type of storage. And then a slightly cheaper type of storage is call data. It's only available for one transaction, but therefore it's cheaper. Recently, there's been a third, even cheaper tier of storage called data availability services. So I'm going to call it SDA. And in this case, the data is stored off-chain, and only a commitment to the data is stored on-chain. This is the cheapest tier of storage on Ethereum, but the data is not readable on-chain. So anytime a function wants to access some of this data, the caller has to provide opening proofs with respect to that on-chain commitment, as well as the data. So looking back at the 3 approaches we saw at the beginning of the talk, let's look at the storage considerations. So in verifiable computation, ignoring y, we have to post the proof pi in the call data. So we have to take up pi amount of call data. In the case of fraud proofs, in the optimistic case, again, ignoring y, there's no data, no storage at all required. In the case of a dispute, we might have to use part of the witness to resolve the dispute. And so the parties will have to supply parts of or all of the witness in the call data. In the case of Naysayer proofs, again, ignoring y, we always have to post pi in persistent storage. So that can be quite expensive. And in the case of a dispute, the Naysayer would have to provide pi nay, the Naysayer proof, in the call data. So it costs some call data as well. So the availability of SDA gives us the following optimization. So instead of posting pi completely on-chain, instead of the prover posting pi completely on-chain, it can just post a short commitment, here represented by this hash of pi. So that's much smaller than pi. And it actually stores the full data of pi in this DA storage, which is much cheaper. And then in the case of a dispute, the Naysayer will again provide the Naysayer proof and also the openings of the relevant pieces of pi in SDA that are required to verify the Naysayer proof. So the call data has been increased slightly in the case of a dispute, but we've reduced tremendously the amount of data required in most cases that needs to be stored in permanent storage. this concludes the talk. To summarize, we introduced Naysayer proofs, a new paradigm for verifying off-chain computation that can lead to significant savings on-chain in on-chain computation. We see a lot of different interesting directions left to explore in this space in terms of mechanism design, cryptography, applications, and maybe more. I strongly encourage you to read the full version of our paper online on ePrint, and feel free to reach out to any of us with questions, comments, or anything else. And I look forward to seeing you at the conference.